In this video, we are going to be going over section 3.6, rational functions. So first off, we have some properties of rational functions. So a function whose rule is a quotient of two polynomials, that is p of x over q of x. So if we ever have a function f of x that is equal to such a quotient, then we say that f of x is a rational function. And we require that q of x is not the zero polynomial, so q of x is not, just equal to zero. And f of x is going to be undefined at x such that q of x is equal to zero. So when we're going and talking about the domain of a rational function f of x, well, we want to exclude from the domain all x values that make the denominator equal to zero. And so if we start out with a rational function just given to us by an equation, and that equation is in unfactored form, what we are going to want to do to determine the domain is factor the polynomial in the denominator, q of x. And then once we have it fully factored into all of its binomial factors, we want to set each of those binomial factors equal to zero, solve for x, and then those are going to be the x values we exclude from our domain. So it's like we start out with all real numbers, or from minus infinity to infinity for the domain, but then we want to subtract from that interval any of the x values that cause the polynomial in the denominator to be equal to zero. And so if a number c makes the denominator zero, then again, that's going to be a value we exclude from our domain. But numerator non-zero, then the line x equals c is going to be a vertical asymptote. And if a number c makes both the denominator and the numerator zero, well, we still exclude that value c from our domain. But instead of having a vertical asymptote, well, we are going to have a removable discontinuity at x equals c. Yeah, I don't really like how I worded this here, but it should say, then we have a removable discontinuity at x equals c. Key point being that with vertical asymptotes, we write x equals c because that's an equation for a vertical line. And with the removable discontinuities, that's like a point that has been essentially deleted from the graph. Because again, we aren't allowed to include any x values in our domain that cause the denominator to be equal to zero, regardless if the numerator is equal to zero at the same time for that value of x. And if the graph of a function approaches a horizontal line very closely when x is very large or very small, we say this line is a horizontal asymptote. Okay. And so now for a little bit about horizontal and slant asymptotes. So for a rational function f of x, which is equal to p of x over q of x, where the leading term of p of x is a times x to the n, and for q of x, it is b times x to the n. We have that if n is less than m, so if the degree of p is less than the degree of q, then the x-axis, or rather the line y equals 0, is the horizontal asymptote. And if n is greater than m, so if the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator, then there is no horizontal asymptote, but there is going to be a slant asymptote, which is given by the quotient resulting from dividing p of x by q of x. So in the case that the degree of p of x is greater than the degree of q of x, what we want to do is, well, that means there's going to be a slant asymptote. And so in order to find it, we want to go ahead and use either polynomial long division or synthetic division to figure out what the quotient from dividing p of x by q of x is going to be. And then what we get for the quotient is going to be some polynomial expression. and that's going to give us the expression for our slant asymptote. It's going to be y equals whatever that quotient is. And if n is equal to m, that is if p of x and q of x have the same degree, then y equals a over b is the horizontal asymptote, where a and b is just, a over b is just the ratio of the leading coefficients, because we said, well, the leading terms for the two polynomials p and q are a times x to the n and b times x to the n respectively. And so just looking at the ratio of their coefficients, it's going to be a over b. So if n is equal to m, then y equals the ratio of the leading coefficients is going to be the equation for the horizontal asymptote. Okay. And so let's start getting into some of the examples. So in these first three examples, we're just going to be given an equation for a rational function, and we are going to try to use these equations or formulas to find the domain for the rational function, and then also give equations for the vertical asymptotes, horizontal asymptotes, and slant asymptotes. And remember, if there is a horizontal asymptote, there's going to be no slant asymptote. And if there is a slant asymptote, there is going to be no horizontal asymptote. All right, so for our first of these three examples, we are looking at the rational function f of x, which is equal to x minus 3 over x squared minus 2x minus 3. So the first thing we want to do, since we're trying to determine what the domain is, as well as what the vertical asymptotes are, is we are going to want to factor this polynomial, which is a quadratic, down here in the denominator for f of x. So we want to try to factor x squared minus 2x minus 3. So we can use the AC method here. So we would have 1 times minus 3 for a times c, which is negative 3. And we want to find two factors of negative 3 whose sum is a negative 2. So we could look at negative 1 times 2, or we could look at 1 times negative 2. Of course, in the first case, we would have, negative 1 times 3, or 1 times negative 3. So in the first case, we would have minus 1 plus 3 for the sum, which is going to be a positive 2. So that's not going to be the two numbers we use for the AC method. And then looking at the other factorization, 1 times negative 3, that's going to give us 1 plus negative 3, or negative 2 for the sum, which is equal to b. So we would use this for the AC method numbers. And since the leading coefficient of this quadratic in the denominator is 1, we can go ahead and use the fast version of the AC method. So we will have x minus 3 over x plus 1 times x minus 3. Okay. And so for the domain, well, we would want to set each of these factors equal to 0 and solve for x. So let's do that. X plus 1 equals 0. And then subtracting 1 from both sides is going to give us x equals negative 1. And then we look at x minus 3, set that equal to 0, add 3 to both sides, and we're going to get x equals 3. So we want to exclude negative 1 and 3 from our domain, so it's going to be the interval from minus infinity up to negative 1, then set union, and pick back right up on the other side of negative 1, the interval from negative 1 to 3, and then set union, the interval from 3 to infinity. So writing our domain in this way makes it so that we are including all real numbers except for negative 1 and 3. Again, when we have parentheses at the endpoints, that means that we aren't including those endpoints in our intervals. So none of these intervals include negative 1 or 3, but the union of all three of them includes all real numbers except for those two. So that's our domain. Okay, and then vertical asymptotes. So VA, well, since we have a common factor of x minus 3 in both the numerator and the denominator, that's going, so x equals 3 is going to correspond to a removable discontinuity. So there's going to be a hole in the graph of f of x at x equals 3 because we have a removable discontinuity there. So we don't have a vertical asymptote at x equals 3 because we have this common factor of x minus 3 in the numerator and the denominator. But with x plus 1, so there is no factor of x plus 1 in the numerator, so that is going to give us a vertical asymptote, which is going to be the vertical line x equals -1. Okay, and then, so if we look at the degree of the numerator versus the degree of the denominator, so in the numerator we have a degree 1 polynomial, and in the denominator we have a degree 2 polynomial. So we would say, how about we write things like this? We'll say, we'll keep using like we said above. We'll refer to the exponent of the leading term of the polynomial in the numerator as n, and the exponent of the leading term of the polynomial in the denominator as m. So we'll say, okay, n here is equal to 1, which is less than 2, which is equal to m, the degree of the polynomial in the denominator. And so since 1 is less than 2, well, according to what we said about horizontal and slant asymptotes, we are going to have a horizontal asymptote with the line y equals 0. And yeah, I'm going to be abbreviating in these examples, VA for vertical asymptote, HA for horizontal asymptote, and SA for slant asymptote. So horizontal asymptote, y equals 0. And slant asymptote, none, for D and E. All right. So for example 2, we are now looking at the rational function x squared plus x minus 2 over x minus 3. And so the first thing we should do, just to make sure that we don't have a factor of x minus 3 in the numerator, or at least to determine if like we're going to have a vertical asymptote at x equals 3 or a removable discontinuity there, what we can do is we can go ahead and let's factor the numerator. So it might seem like we don't necessarily have to in these examples because of what we're being asked to find. Of course, if we were being asked about the x-intercepts, we would want to factor the numerator. because, well, the x-intercepts are going to be where the function's value is equal to 0. And so if we factor the numerator and we find all the binomial factors there, well, we can just find the zeros of f by just setting each of those binomial factors in the numerator equal to 0, solving for x, and that'll give us the x values where our function's equal to 0. So if we were being asked about the x-intercepts, then of course we would want to factor the numerator because we want to see what binomial factors there are there, so we can find these zeros for f, which correspond to the x-intercepts. But here we're just factoring it to make sure that none of the factors in the numerator match with the factor in the denominator. So that way, when we are talking about vertical asymptotes, we can properly discuss, if there is a vertical asymptote at x equals 3 or not. So factoring the numerator, we would have, so for the AC method here, we would have 1 times -2, which is going to be -2. And we would want to find two factors of -2 whose sum is a positive 1. And so the two factors that do that for us are going to be positive 2 times -1, because we'll have -2 for the product and then positive 1 for the sum. So this tells us that x squared plus x minus 2 factors as x plus 2 times x minus 1, and then over x minus 3. So we don't have any removable discontinuities here. And yeah, in general, when you're dealing with rational functions, if you're given an equation for the function and it's in unfactored form, you should factor both the numerator and the denominator first, because not only does it matter for being able to distinguish vertical asymptotes from removable discontinuities, but also it's important for distinguishing x-intercepts from removable discontinuities, because we could have like, for instance, like in this previous example, like if we were asked about the x-intercepts, we might be tempted to say, well, f of 3 is equal to 0 because 3 minus 3 is equal to 0. But that would not take into account the fact that we have this factor of x minus 3 down in the denominator. So that's not actually an x-intercept of f of x. So if we ever have a common factor in both the numerator and the denominator, then that common factor does not correspond to a vertical asymptote, and it does not correspond to an x-intercept for a rational function. All right, so for the domain, well, we would take x minus 3, set it equal to 0, and we would find that x cannot be equal to 3. And so for our domain here, it's going to be all real numbers except for 3. So we'd go minus infinity to 3, and then union 3 to infinity. Okay, and then vertical asymptotes. Well, we are going to have one at x equals 3 this time, and that's the only factor in the denominator is x minus 3, so we only have one vertical asymptote. And then horizontal asymptote, well, here we have that the degree of the numerator is 2, and the degree of the denominator is 1. And so we said in that case there is going to be no horizontal asymptote, but there is going to be a slant asymptote. So HA, and yes. Oh man. So I'm realizing we're going to run out of vertical space here, so I'm trying to move things around real quick. So here for horizontal asymptotes, since the degree of the numerator is 2 and the degree of the denominator is 1 and 2 is greater than 1, there is going to be no horizontal asymptotes, D and E. So we only have a horizontal asymptote if the degree of the numerator is less than or equal to the degree of the denominator. Slant asymptotes, here we do have one. So let's go ahead and figure out what this slant asymptote is supposed to be using synthetic division. So we are going to synthetically divide x squared plus x minus 2 by x minus 3. So we will write a 3 and then make our little synthetic division table, kind of small for space. And then for our coefficients, we'll have 1, 1, minus 2 for the dividend. So we'll bring down the 1, multiply that by 3, add that to 1 is going to be 4, multiply 4 by 3 is going to be 12, add that to minus 2 is going to be 10. So 10 is the remainder, but we don't really care about that. What we care about here is the quotient. So reading the quotient here, it's going to be 4 for the constant term, and then next is the degree 1 term, so it's just a 1, so we're just going to have an x. So our quotient is x plus 4, so our slant asymptote is y equals x plus 4. All right, and then next we have the rational function x minus 2 over x minus 3. So the first thing we want to do is talk about the domain. Well, again, since we just have this factor of x minus 3 down in the denominator, our domain for this third example is going to be the same domain as from the previous example. It's going to be from minus infinity to 3, set union from 3 to infinity. So all real numbers except for x equals 3. And then vertical asymptotes. Well, again, since we don't have any factors in common between the numerator and the denominator, the one factor in the denominator is going to correspond to our one vertical asymptote, which again is going to be given by the equation x equals 3. Horizontal asymptotes. So here we have, whoa, I thought I copied this. So here we have that the degree of the numerator is equal to the degree of the denominator. And so we said that in that case, we are going to have a horizontal asymptote given by y equals the ratio of the leading coefficients. So y equals 1 over 1 here would be that ratio, or rather just y equals 1. And then slant asymptotes, well, since there is a horizontal asymptote, there is no slant asymptote, so D and E. All right. In the next example, we are asked to write an equation for a rational function with the given characteristics. So it has vertical asymptotes at x equals -4 and x equals -1. So this is telling us what binomial factors we should have in the denominator. We're going to have a binomial factor of x plus 4 and a binomial factor of x plus 1. X-intercepts at the points 1, 0 and 5, 0, and a y-intercept at 0, 7. So if we start out by letting f of x be equal to p of x over q of x, might do it, write that over here actually. Then, so if we're thinking about f of x as being the ratio of p of x over q of x, then what we're being told about the vertical asymptotes here is that q of x has factors of x plus 4 and x plus 1. And then here with the x-intercepts at 1, 0 and 5, 0, well, since f of x is equal to 0 when x is equal to 1 and when x is equal to 5, that means p of x is equal to 0 when x is equal to 1 and when x is equal to 5. And so this means that it must have a factor of x minus 1 and x minus 5. So it's important that if you are trying to build the factors for the polynomial in the denominator by just being told like the vertical asymptotes or the values that are missing from the domain of our rational function, to flip the signs for those x values when writing the factors. So you want to write x and then plus whatever number you have for either your vertical asymptote or, the domain value that's missing, changing, so plus whatever that value is, with its sign changed. Yes. And same thing with the x-intercepts for p of x. So we'll have x minus 1 and x minus 5. Okay, and then we're going to use this information about the y-intercept to figure out what the leading coefficient is. So we can go ahead and write f of x is equal to a times x minus 1 times x minus 5 over x plus 4 times x plus 1. And yeah, I just realized I want to use like a single value for this coefficient here. So the leading coefficient isn't going to be like a single number. It's going to be like a ratio of two numbers, but when we're solving for it, of course, just so we don't lose our minds, we want to think about it as just being like a single variable. So we'll just use a there. So I should not have made these adjustments. All right, so now we have an equation for f of x up to finding the value for the leading coefficient a. And so this is where we're going to use the information about the y-intercept. So since we have a y-intercept at 0, 7, this is telling us that f of 0 is equal to 7. And so we can go, okay, so 7 is equal to a, and then we'll just plug in zeros for x. So 0 minus 1 times 0 minus 5 over 0 plus 4 times 0 plus 1. And then from here, we want to simplify. So 7 is equal to a times, so we'll have minus 1 times minus 5 is going to be 5. And then over 4 times 1 is going to be 4. And so solving for a, we end up with a is equal to 28 over 5. That's after we multiply both sides by 4 over 5 to get a by itself. So 28 over 5. And so f of x is equal to 28 times x minus 1 times x minus 5 over 5 times x plus 4 times x plus 1. All right. In the next example, we are going to be given an equation for a rational function, and we are going to try to use that equation to graph it. So to graph a rational function, we want to find any vertical asymptotes and horizontal asymptotes, as well as any x-intercepts, because that'll give us at least points that the graph will pass through. And then we want to draw the items from the first step on a coordinate grid. And to remember that the asymptotes are like dotted or invisible lines. So they aren't an actual part of the graph. They're more just like a feature. And most graphing utilities don't actually graph the asymptotes because, again, they're just like these invisible objects. Since it's kind of hard to use dashed or dotted lines in my tablet, I'm instead going to draw lines using the highlighter tool. So that way they're kind of like invisible looking. So that's step 2. And then for step 3, we are going to plot a point in each interval of the x-axis created by the x-intercepts and the vertical asymptotes. So it's kind of like the x-intercepts and the vertical asymptotes are going to like partition the x-axis, and we just want to find points on either side of like a vertical asymptote or an x-intercept. That way we just have a few other points plotted that the graph of our rational function will pass through. And then we want to use the information and points from 3 to finish sketching our graph by just connecting those points in a smooth fashion and extending them so that they approach the vertical and horizontal asymptotes. So the rational function that we are going to try to sketch is going to be f of x equals 3x squared over x squared minus 4. So the first thing we should do is factor. So 3x squared, just write it and leave it as is, and then x squared minus 4, so we have a difference of squares down there, and we know from the difference of squares factorization formula, this is going to factor as x minus 2 times x plus 2. And so we have vertical asymptotes, 1 for the factor x minus 2, set that equal to 0, solve for x, we'll get x equals 2 after adding 2 to both sides, so that's one of our vertical asymptotes, x equals 2. And then for our other one, set the other factor equal to 0, solve for x, and we get the equation for our other vertical asymptote, x equals negative 2. Okay. And then for our horizontal asymptotes, well, here we have that the degree of the polynomial in the numerator, call that n, is equal to 2, and the degree of the polynomial in the denominator is also equal to 2, and we'll call that m. So n is equal to m here. And we said in that particular case, we are going to have a horizontal asymptote at y equals the ratio of the leading coefficients. So here y equals 3 over 1, or just y equals 3. And because of that, there are going to be no slant asymptotes, D and E, because there is a horizontal asymptote. And then for the x-intercept, well, if we set x equal to 0, well, then 3x squared here in the numerator is going to be equal to 0, because we're going to have 3 times 0, which is going to be 0. And then in the denominator, we're going to have 0 minus 4, or just minus 4. So we have 0 over minus 4, which is going to be 0. So f of 0 is 0. So we have an x-intercept at the origin. So let's go ahead and draw our asymptotes and plot our x-intercept. So I'm going to do the vertical asymptotes, I guess, in red. See how thick this looks. Okay, it's a good thickness. Okay, so we have vertical asymptotes at x equals -2. And x equals 2. So that's what these kind of red opaquish lines are our two vertical asymptotes. And then we have a horizontal asymptote, which I'm going to do in pink, at y equals 3. So there's the horizontal asymptote. You can write their equations off to the side if we want. Okay, and now for the actual graph. So let's start plotting some points. So we have the x-intercept at 0, 0. Let's go ahead and calculate what f of -1 is going to be. By the way, so just because, so if we look at the polynomial in the numerator and the denominator, we don't have any, so they're both degree 2 polynomials, and they are both missing their degree 1 terms, their linear terms. And so what this is going to mean to us is that when we go and calculate like f of, say, like -1, well, it's going to be the same as f of 1. And we can see that again by just realizing, well, if we have a negative, we're just going to square it, and it's going to become a positive anyways. So this can kind of streamline us being able to plot the points here, because we'll be able to kind of calculate two values at once. So first, let's do f of -1, which is going to be equal to f of 1, which is going to equal 3 times 1 over 1 minus 4, which is going to equal, well, 3 over -3, which equals -1. So we're going to have points here and here. And then let's go and plot some points on the other sides of the two vertical asymptotes. So let's find f of -3. And from what I just said, that's also going to be equal to f of 3. So that'll give us 2 more points. So f of 3, which is equal to f of -3, is going to equal 3 times 3 squared, or -3 squared. In either case, we end up with 3 times 9 over, and then 3 or -3 squared is going to be 9 minus 4. So we end up with 27 over 5, which we can write in decimal as 5.4. So this means, so go over to x equals -3, and we'll have a point right about here, and go over to x equals 3, and we'll have another point right there. All right, and from here, we just want to go and kind of, we'll connect our points in a smooth fashion, and I realize there's really nothing to connect to the left and to the right of our first vertical asymptote and second vertical asymptote respectively. But what we will do is, so we already have our points there, and all we're going to do is just start graphing from these points by going towards the vertical asymptote and going towards the horizontal asymptote. Because when it comes to asymptotes, again, these are just invisible lines that our graph will approach, but never cross or touch. So they'll get very close to them, but they'll never cross or touch them. And so it's that knowledge that since they are asymptotes, that the graph will approach them. So just knowing where the points lie is kind of enough for our purposes, because we do want to at least know if the point's going to be like above the horizontal asymptote or below. And since we already know where it is in relation to the horizontal asymptote, or where these 2 points are in relation to the horizontal asymptote, we can go ahead and complete the graph. So again, just kind of graphing things so that it looks like it's approaching the horizontal asymptote to the left of its first vertical asymptote. And there's our graph. I'll be happy with that. Okay. So there is like a continuation to this example, but first we are going to discuss like the arrow notation. So when we are talking about limits, we will often write things like, so if we ever have x and then arrow to a with a minus in like the exponent, this just means that x approaches a from the left. So x is less than a, but close to a. And then if we have x goes to a, but with a positive sign or a plus sign in the exponent next to a, this means that x approaches a from the right. So x is greater than a, but close to a. And then x and then arrow to infinity, this just means x approaches infinity, so x increases without bound. X arrow to minus infinity, x approaches negative infinity, so x decreases without bound. And then we have x goes to infinity, so the output, f of x arrow to infinity, so the output of f approaches infinity, or in other words, the output of f of x increases without bound. Then we have f of x and then arrow to minus infinity. This just means that the output of f of x approaches negative infinity, or in other words, the output of f of x decreases without bound. And then we have f of x arrow to a, which just means that the output of f of x approaches a. So we want to, in this next example, use approaches arrows to describe the local and end behavior of the function above. So for the local behavior, we mean what is the function's values doing when we're close to the vertical asymptotes. So near the vertical asymptotes. So let's go back to our graph. to the graph. So looking at our graph here, well, as x approaches -2 from the left, we have that f of x is tending to plus infinity because the function's values are just increasing without bound. And that's as we, let me get the laser pointer here. So that's as we approach the vertical asymptote. So this is x going to a from the left. And then on the other side of the vertical asymptote at x equals -2, we can again hop on our graph and go towards that vertical asymptote, except from the right now. And what we're seeing as we approach that vertical asymptote from the right, so as x goes to -2 from the right, well, the function's values are decreasing without bound now. Okay, and then now if we approach the other vertical asymptote at x equals 2 from the left, well, we see again here in this case that the function's values are decreasing without bound. So f of x is going to -infinity again. And then on the other side of that vertical asymptote at x equals 2, let's go ahead and approach 2 from the right now. And so approaching 2 from the right, well, we see from the graph of f of x that the function's values are increasing without bound. So f of x is going to infinity as x goes to 2 from the right. Let me go ahead and write. This is the graph of f of x. So here we would be going like x approaches -2. Actually, let me do it for +2. So this is 2 from the left, so 2 minus. We'll put it down by the actual graph. Then over here, we have, this is where x goes to 2 from the right. All right, so we said that as x approaches -2 from the left, f of x goes to infinity. So we have f of x goes to infinity as x goes to -2 from the left. And then we said that when f of x, or as x goes to -2 from the right, f of x goes to -infinity because it decreases without bound. Okay, and then for the other vertical asymptote, we said that f of x goes to -infinity as x goes to +2 from the right, or sorry, from the left. That's what we saw here. So going towards 2 from the left, well, we see the function's values are decreasing without bound. So f of x goes to -infinity. And f of x goes to infinity as x goes to 2 from the right. So that's the local behavior. And then for the end behavior, well, that's essentially given to us by the horizontal asymptote. So here, if we look, so as x goes to -infinity, or as x goes to infinity. Well, in either case, if we're writing along the graph of our function here, well, it's just going to be getting closer and closer to 3. So the values of f of x are getting closer and closer to 3 as x goes to minus infinity and as x goes to infinity. So f of x goes to 3 as x goes to minus infinity, and f of x goes to 3 as x goes to infinity. All right. Okay. And so we have one more example that I'm going to have us look at, and it's similar to question 26 in the Lumen homework, though when you're doing question 25 as well, you're also going to want to pay attention to this example here. And I have looked at the textbook, and the textbook does kind of explain how to do these two problems because they are a bit difficult without kind of viewing like the particular assumptions the textbook wants you to make. We are asked in this problem, in this version of question 26 from the rational functions Lumen homework assignment, to write an equation for the function graph below. And we are told that the y-intercept is at 0, 1/12, and the x-intercept is at 1, 0. And so what we can do here is, well, with this x-intercept, so the book basically expects you on problems 25 and 24 to not just determine the factors for our rational function in both the numerator and the denominator, but also to determine the degree of those factors. And it's either going to be degree 1 or degree 2, or sorry, the exponent for those factors. It's either going to be 1 or 2 based on the graph. And so the way we can determine if a factor is going to have an exponent of 1 or 2, well, when it comes to the factors in the numerator, well, those are going to correspond to the x-intercepts. And so we just want to check the x-intercepts. And if the graph of our function just goes and touches the x-axis and bounces back in the other direction at one of the x-intercepts, like a quadratic function would, then we want to assume that the exponent corresponding to the factor of that x-intercept is 2. And when it comes to the factors in the denominator, so if we look at the vertical asymptotes, those are going to give us the factors for the denominator, or for the polynomial in the denominator for a rational function. And then we also have to determine if the exponent for each of those factors is 1 or 2. And the way we can do that is, well, if around the vertical asymptote, we are having that the functions like it has opposite behavior. So for the vertical asymptote at x equals -3 here, if we look at the graph of our function in black, well, it goes to minus infinity. F of x goes to minus infinity as x goes to -3 from the left. And f of x goes to infinity as x goes to -3 from the right. And so since they have opposite behavior around that vertical asymptote, what we are supposed to assume based on that is that the graph is that the factor corresponding to this vertical asymptote has an exponent of 1. And then if we look at our other vertical asymptote here at x equals 2, well, since the graph has the same behavior on either side of this vertical asymptote, that is f of x goes to infinity as x goes to 2 from the left and as x goes to 2 from the right, this means that the factor corresponding to this vertical asymptote has an exponent of 2. So if we see an x-intercept where the graph of our function just intersects the x-axis and then crosses to the other side, we are going to assume that that x-intercept corresponds to a factor in the numerator with an exponent of 1. And if we see an x-intercept where the graph of our function just goes down and touches the x-axis but doesn't cross to the other side, it just bounces back, then we are going to assume that the factor for that x-intercept has an exponent of 2. And then for the factors in the denominator, we're just going to look at the vertical asymptotes to find those guys, and to determine their exponent, we're just going to see if the function has opposite behavior depending on which direction it approaches that vertical asymptote in. And in that case, if it does have opposite behavior, the exponent's 1, and if it has the same behavior, then the exponent's 2. All right. So looking at the x-intercept, again, we're told it's 1, 0. So f of x, is going to equal, and then we're going to write a. We're going to have to solve for that leading coefficient like we have had to in previous problems. And then since we only have one x-intercept at x equals 1, this means we have a factor of x minus 1 in the numerator. And again, looking at the graph here, since the graph of f just goes down to the x-axis and doesn't cross it at that x-intercept, we're going to assume the multiplicity at that x-intercept is 2. So the exponent on that factor is 2. So we have x minus 1 squared in the numerator here. And then for the denominator, well, we have x plus 3 for the vertical asymptote at x equals -3, and x minus 2 for the vertical asymptote at x equals 2. And since around the vertical asymptote at x equals -3, the function has opposite behavior, we are going to say that the exponent on that factor is 1. And then since around the vertical asymptote at x equals 2, the function has the same behavior, we are going to say that that factor has an exponent of 2. Okay. So this is what our function from the graph looks like up to solving for a, which is where we're going to use the information about the y-intercept. So f of 0 equals 1 over 12 means that 1 over 12 equals a times 0 minus 1 squared over 0 plus 3 times 0 minus 2 squared. And so we have that 1 over 12, just simplifying what we have on the right, equals a, and then we're going to have minus 1 squared, which is going to be 1 over 3, and then times -2 squared is going to be 4, so 3 times 4. So we have 1 over 12 equals a times 1 over 12, and so a is equal to 1. And so we can write f of x is equal to x minus 1 squared over x plus 3 times x minus 2 squared. But please do be careful when you're doing questions 25 and 26 from this homework. Pay attention to how the graph of your function is intersecting the x-axis at any of the x-intercepts, because if it's crossing, then you are going to want to use an exponent of 1 for the factor corresponding to that x-intercept. And if it's not crossing, it's just going and touching the x-axis, you're going to want to use an exponent of 2 for the factor corresponding to that x-intercept. And then similarly for the factors in the denominator, you are going to want to look at the vertical asymptotes to find those, and then to determine the exponent on each of those factors, if it's 1 or 2, you're going to want to check, okay, does the function have opposite behavior on either side of the vertical asymptotes. If it does, then the exponent corresponding, or the exponent on the factor corresponding to that vertical asymptote is going to be 1. And if it has the same behavior on either side of the vertical asymptote, then the exponent on the factor corresponding to that vertical asymptote is going to be 2. So it's going to be 1 or 2, and that's kind of how we can determine it from its graph.